Welcome to 10.6 Exponential Growth and Decay. So first, a couple of potential formulas. We have for exponential decay, y equals a times the quantity 1 minus r to the t, where a is initial amount, r is rate of decrease, t is time. We have y equals a times e to the negative kt, where k is a constant. For exponential growth, we have y equals a times 1 plus r to the t, and y equals a times e to the kt. For all of these, y is the amount after t time for all equations. Okay, so let's try our first example. Example 1, a cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for half of this caffeine to be eliminated from a person's body? So we're going to use the formula y equals a times 1 minus r to the t. We're typically going to be given this equation. We just need to know how to substitute values in. So first, our a, our initial amount, is 130. Our y is what we want out after it, which is half of the caffeine, which is 65. Our r is 0.11. And our t is what we are going to be solving for. Okay, if we divide by 130, we get 0.5. 1 minus 0.11 is 0.89. And then we're going to solve this as a normal logarithm. So we're going to do log base 0.89 of 0.5 equals t. And then we do change of base, log 0.5 divided by log 0.89, which gives us about 5.95 hours. Okay, so that's our first example. Our next one, the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to become disintegrated. All life on Earth contains the radioactive element carbon-14, which decays continuously at a fixed rate. The half-life of carbon-14 is 5,760 years. That is, every 5,760 years, half of a mass of carbon-14 decays away. So what is the value of K for carbon-14? So we're going to use the formula because it is half-life, it is decaying. We're going to use y equals a times e to the negative kt. We're looking for half, so our a in this question doesn't really matter. Our a is just a, and our y is 0.5a because we're trying to get half of it. K is what we're solving for. T is 5,760. Okay, so we're going to divide by a and we get 0.5. And then we're going to solve this like a normal logarithm. We're going to take the natural log of 0.5 and the natural log of e to the negative 5,760. So that gives us negative 5,760k equals natural log of 0.5 divided by negative 5,760. And we get about 0.00012. That is our constant for carbon-14. So let's use that to solve our next problem, where a paleontologist is examining the bones of a woolly mammoth, estimates that they contain only 3% as much carbon-14 as they would have contained when it was alive. So how long ago did the mammoth die? Again, we don't know A, but we know that Y is 0.03 of A. And we're using our K this time as 0.00012. We don't know t. We're going to divide by a and it cancels, so 0.03 is equal to e to the negative 0.00012 t. Take the natural log of both sides, and we get negative 0.00012 t equals natural log of 0.03 divided by 0.00012 and then that gives us about 29,221 years. Okay, our next example, in 1910, the population of the city was 120,000. Since then, the population has increased by exactly 1.5% per year. If the population continues to grow at this rate, what will the population be in 2010? So we're going to use y equals a times 1 plus r to the t. A is 120,000. Y is what we're trying to find. From 1910 to 2010 is 100 years, so that's our t. And our rate is 0.015. Okay, we can go ahead and just type all this into the calculator, but 1.01015 is 1.015. But again, we just type this into the calculator. 120,000 times 1.015 to the 100th power is 531,845 people. Our last example, as of 2000, China was the world's most populous country with an estimated population of 1.26 billion people. Population of China can be modeled by C of t equals 1.26 e to the 0.009 t. According to this model, what is China's population in 2017? So that is 17 years later. We're going to put that in for t. We're going to go ahead and multiply 0.009 and 17 and get 0.153. And then we're going to type that in our calculators. 1.26 e to the 0.153. And we get about 1.47 billion people. Alright, that is it for the applications of growth and decay of exponential functions. Good luck on the practice.